Hello. Try that. Hello, everyone. Oh, you are so much. Thank you for the invitation. Thank you, everyone, for being here. Thanks, Supercell security team, for giving us the chance to speak about what we did during the last year. The topic of today is reverse engineering on Android, and we are going to show and give you a gentle welcome, showcasing some very basic stuff. So we are going to give you a little introduction on TCP protocols. A couple of TCP protocols we reversed in the last year. And later, we are going to see a couple of examples on how to instrument both the Java side and the native side, so that we will arrive at the challenges, which is the focus of this talk, and which will see a real usage case of all the stuff we will see during the talk. So this talk will be based mostly on live demo. So we will run a lot of stuff, and we will have just a couple of slides. So please, let's go. And let's start by saying why we do hack games. Oh, sorry. First, I have to say that me and Vincenzo, I'm sorry if I didn't introduce us. We are from Italy. My name is Giovanni, and this is Vincenzo. We are both employed at the Overwolf mobile team. I am an Android developer. He is mostly backend. And whatever we will say today is not linked in any way with our company, nor company linked with it. So yeah, let's go on. And why we do such stuff on games mostly? Because games are usually heavily protected with different kind of protections and different encryptions or compressions methods. And so they have some extreme hard logics to reverse and understand. So this will give us fun. So as you all are hackers, you understand that the challenge is what pushes us to do our best. And also because with the reverse engineering work on mobile games, you will be good later to build a lot of different projects, like statistics, in example, which is mostly what we do in Overwolf, and a lot of cool other different projects. So in these 3 slides I've prepared, there are some of the most used games, most downloaded and most played games of the last year. And the slides will highlight how big companies decide to build their security with different methods, but also the protocol with different structure, which is usually what we target. Okay, this is lineage 2, an example which we will see later in details. And these are the tools we love to use, some of the tools we love to use, and some of the tools we are going to run today, which include my favorite one, which is Frida. Did anyone of you know Frida or used Frida back anytime? No? Cool. Something new? Nice. We will quickly see how to attach GDB with my favorite extension, which is Jeff. And later some minor tools which we use on Android, and unicorn emulators as well, which is what made me won my last challenge with Supercell. Okay, we will now run our demo. I've prepared for today a big project divided by steps. So I hope everyone will be able to read it fine. And the first step I've prepared is something quick that I want to show, and that is usually what we deal with. There are a couple of examples of TCP protocols. Please zoom it a bit, if you can. Yeah, cool. OK. Those are two encrypted messages coming from two different games. And usually what we do is converting something like this into something more readable, like this. Informations on such stuff are mine, so feel free to use my token to log in the games. I don't care, it's good. And so, once we have something like this, we want to later transform it to something like this, which is a bit more readable and which is ready to be stored on our database and later served with any kind of service your imagination can create. So, the first thing you will meet if you attempt to approach on reverse engineering on mobile in general, but also, in this case on Android, is to obtain the pseudocode and read the content of the source, of course. And to do this, I've prepared a little example. This is a report that's coming from a framework, open sourced on my GitHub. So if you want to take a better look to it, you can do it anytime. This report, it's meant to give you a first understanding about the application's behavior, and including network requests, files open, so you can check if the applications are doing something bad, or an example we use to check network requests. So we will quickly go into network requests, which is what we want to show now. And OK, we can see that this mobile app tracker is sending something encrypted, which is not readable at the moment. And we are now going to understand how we can quickly use Frida to read this message. OK. Also, we will see some pieces of code about it. Let's. OK. OK. Now, we are using the API key tool and Dex2Jar first to unpack the applications and obtain the pseudocode. API key tool is used to being allowed to access the resource of the application, so it's not really helpful to read the code. The other tool is instead Dex2Jar, which is what we need to read actually the pseudocode of the application. And once we got an output from Dex2Jar, we will feed another applications, which could be any app which is able to read Dex. There are a lot open sourced also. My favorite, it's called Luiten. And so this is the result. We can see all the code, the Java code, which is not usually where the magic stuff happens, but we want to cover everything. So let's go into our interest package, which is COM mobile app tracker. And without going so far, we immediately see that there is a class which is very interesting, called mate encryption. So we can also look at all the methods, and we can find inside two interesting methods, which are encrypt and decrypt. So for this quick demonstration, we are going to take what is the argument of this function, which is some of the very first reverse engineering thing. If we want to know how is a function working, and so we are going to run Frida and dump this argument. So this is a piece of code which I've prepared. And of course, this is open source as well. So I invite you, everyone, if you are interested, to check all the methods. Now we have not so much time to explain everything. So we are just using a Frida API to immediately trace that function and dump the argument. So please, Vincenzo, run this. We are going to it very quickly because, yeah, I know Java hooking is pretty boring and it's pretty easy stuff, at least for me. And yeah, it's not very fun, but let's go. OK, please show also the screen. So yeah, everything, it's live and it's not recorded. Go on.
Moment problem, sorry. The beauty of the live.
Give it to me. Sorry, we forgot to run Frida. OK, go for it, please. Let's run it once again. No, sei lì. No, Dio, l'hai killato. Okay, sorry for this delay. We didn't start Frida on the phone, so okay. No. Go on, please. Non è quello custom. Cool, finally we can do it. OK, cool. Now, our function is being invoked, and we just dump the encrypted content inside it. So this was pretty easy if we had Frida running, of course, on the device. So Java hooking is pretty easy and boring. So let's go to something more interesting, which is native hooking. And to do so, the example we want to take is on lineage 2. And we are taking this as example because we found it pretty easy also to let you guys understand, also because of some mistake from the developers. So what we are going to do first, vai? OK? Cool. We are still going to use Frida for this because Frida make very easy to use native stuff and see the content of the methods. OK. So inside this script, this is a standard script which is running Frida. And it's usually a JS with a Python script. The Python is bridging the JS and is injecting the code inside the process. So I'm sorry, I'm a bit excited and nervous for this. It's my first time.
We had some problems.
OK, so we got the log, and we got the result. And this is an example of the TCP protocol of lineage 2. As we can see, we got 3-byte headers at the top, followed by an encrypted message, which we actually doesn't know how they are encrypted. So we want to know how this is encrypted. And to do so, Frida also allows you to do a backtrace, which we added at the script. And as we can see, there is a native library which is involved with this. It's called libUE4. And the developer mistake I was talking about, it's that they left the bug symbols inside, which makes everything very, very easy. So we can now use our favorite decompiler, and we can open the library and check if send is actually used in there. Okay? You can see on the left that all the debug symbols are left in place. So we already know where the stuff is happening, and it will take really half an hour of static analysis. So we are going straight to the functions which are involved with these. And we can see a little block of code with two interesting functions, which are update CRC and the XOR, a bit more down, and the XOR encode. These two methods are supposed to be used by the application, but we actually don't know. So we want to verify that that the application is actually using this code and it's not dead code. So how we do so? For doing so, we are going to showcase GDB, which make pretty easy to reach the addresses, also thanks to the debug symbols left on the app. Okay, we are going to attach GDB now to the process, and as you can see, it's not the standard GDB. It's powered by Jeff, which is an extension. I'll give it just 2 seconds to read it. Now, we are going to set a couple of breakpoints, and we are going to read the memory. So we are actually sure that these functions are really used and involved with the encryption. So the first thing we are going to do is taking the address of the functions, which is very easy, thanks to the debug symbols. Otherwise, we would need a less trivial way to access them. Just so. Okay, so we can set our breakpoints and continue the execution of the program. Okay, we got both. Okay, let's go. Please, Vincenzo, show the screen. Cool. So at this point, we know that the game is actually using those functions. So we know what's inside all those registers, and we are giving you some very small examples on how we are going to read them. We know that R0 holds the address of the result, and R1 holds the address of what the CRC function is taking, which is actually our payload. And so we are going to continue the execution to see the XORing, which is called as well, of course. And this time, R0 is holding our payload with 4 bytes more on top of the payload, which is the CRC just built by the flow of the program. So once we know something like this, and we test it a couple of times, it will be pretty easy to rebuild something like that, something like this, which is basically the two functions we did just breakpointed. And please, Vincenzo, show them the keys, which are coded inside the library. And it was really easy for such a big game to to reach the encryption method and the keys of the method. Okay, Giovanni. Okay, and later on, of course, you will arrive to something like this, which is the protocol definition of the game. Okay, which is the protocol definition of the game. Cool. Okay, let's go on. Okay, so sorry if you are going really quick into this, but we really want to arrive to the challenge. So let's go with ARM emulation, a quick overview to ARM emulation. Did anyone of you heard about Unicorn emulator? Okay, cool. And Unicorn emulators allows you to actually emulate instruction, but not only instruction. You can even emulate a whole binary inside. And for give you an introduction to this, I prepared this script, which make very easy to understand how is it working. And what is this doing is creating the emulator context, mapping inside the emulator context two simple instructions which I wrote, basically a sum of some registers. And we are using those test values to verify that it's actually running. So we run it, and cool, we can quit here. Okay, so our results is in R2, and now we will see a real usage case of Unicorn, which we used for emulate 10-cent LZ4 compression, which is pretty different from a standard LZ4 because we didn't manage to obtain the same results from common LZ4 library. So we built this script to reach our goal, and as we can see, it's mostly similar to what we just saw, but instead of writing a simple instruction into it, we are writing a full function, and we are setting up the registers in order to let the function work. Otherwise, we will just have a wrong result, or maybe it will just don't work. So we need to make sure that everything is set up correctly. And also, I've added a little benchmark at the bottom, so we can see how much time the emulator take to run 200 times. So we are going to run it now. Cool. It took less than 1 second to emulate this function 200 times, which is not that good, but it's not that bad. So it also depends on the machine hardware, but we think this is very suitable for production environment. And so pretty cool. Now we will see the heart of this talk, which is the challenge I had with Supercell security team during the last year. Starting from a special FRIDA detection, which the security team coded for me because they know that I love to use FRIDA. They know every stuff I do because I'm used to report to them all the bugs I found, all the stuff I used. And so, it was very funny to tell them that we've managed to break a FRIDA detection with FRIDA. And I'm showcasing this because I want to let you see how FRIDA is powerful in such context, because it allows you to interact with emulators. It allows you to interact with registers and memory during the runtime of the application. So we just saw the app crashing because of this FRIDA check, of course. And Vincenzo ran the app without the script. And instead, if we run the app with with our script, the game will just go and start normally without crashing. So what we basically did in this script is replacing the socket descriptor of the check, because if you start thinking on how a developer on the other side can check if Frida is attached to the process, you would figure out by yourself that there are only two ways, which are checking the memory layout if the Frida gadgets are inside the memory, or trying to check if the Frida socket is up. As Frida work like GDB, so there is a server on our Android device and a client which interact with it. So the easiest way would be to just check if the Frida socket is up and running. There is not really the needed to know that Frida is running by default on the file descriptor 2, but well, it's good for learning purpose and cool. As we can see at offset 26E, the assembly is moving 2 to R0, which is the socket descriptor. And what we did was just replacing this value with something we were sure was something just not connected, not alive, and so on. The game will just start without any problem. Okay? Yeah, we will run it once again. Why not? Let's see, the game will just start fine. Cool. Some other features of Frida we are taking today, as I said, Frida allow you to dynamically play with the memory and the registers. So during the past few months, Supercell introduced to all their games protection commercial, which I believe is powered by Arxan. And we know that it costs from $50,000 to $100,000 per game. So we are also pretty proud to say that we won against this. And this protection has changed a lot of stuff in the game and introduced a lot of protections such as memory CRC, strings encryption, anti-debugging, obfuscation, a lot of stuff to prevent someone like me to do reverse engineering on games. So how we won against this? First, using cool features of Frida. Frida allows you to also dynamically detach from the functions you are intercepting. And as you know, GDB and Frida, like GDB, alter the memory layout in order to work and let you instrument the process. So the protection is detecting that Frida has something attached. So what I want to highlight in this script is the commented line Vincenzo is evidencing on the screen, which is the APA from Frida, which allow you to detach the function. And if we run the game in this state with this script, we will just see that the game will not load and crash because of the protection. So we are going to let you guys see that the game is really crashing. Yep, cool. Now, we are just going to decomment this line. Also, will Vincenzo decomment it? Please take a look at the if conditions on top of it, which is basically a little brute force, okay, we did to understand when exactly this CRC is happening. touching any of those values will make the game crash. And because arcs make very trivial to understand where those CRC are happening. And so we preferred to invent some tricky way to bypass this. And so if we are now going to run this, the game will just start, and the proxy will just do his job. Between this script is a proxy for all their games, which is available as well on my GitHub. So feel free to go anytime to check that stuff out. But yeah, the game is just running, so it's cool. We can close this. OK, cool. So this is where most of the talk is focused, and is what was my last challenge. This is a screenshot, which is just the beginning of the encryption function, not the whole encryption function, so just the beginning. And after we did reverse edit, we get that the change on this, because Clash of Clans actually have a different crypto from all other games, will before the crypto was shared between all the games. Now Clash of Clans is changed, and after the reverse work, we understood that there is a single byte change in all of this. So I challenge everyone here to try to spot with an easy way a single byte change inside all of this messed up. And yeah, in the end, we figured it out. That was pretty easy, but you know, we did a lot of tests, a lot of stuff, and we was debugging also in the wrong direction. And so how we managed to reverse engineer this? By creating a sort of timeless debugging environment using Unicorn engine. So first step, we are going to use Frida. Please show the top of the function. OK? All these offsets you can see, I left these for debugging, was created initially for debugging purpose, and I left these to remind myself all the effort I put on this, because at the first try, I was trying to reverse this using Frida straight, but was pretty impossible because we have a lot of dynamic things inside this encryption. This encryption is taking a caper, so we will just have a different result on every login in example. And this makes the things very hard. And so that we recreate a timeless debugging environment static to allow us to debug it properly and understand what was the change. So this Frida script I've created, please get a bit on bottom. OK. We are attaching to the entrance of the crypto. And what I'm basically doing here is taking a dump of my whole phone memory. So I'm dumping all the memory layout involved on this and saving them into a file. So if we open the testing, we can see the result. We are not going to run this because emulation of a whole function like this, it's always depending on the machine you are running it, of course. But on this machine, it's taking up to 7 minutes. So it's pretty hard to run all of the change we made. So we prepared a log file, which is the result of the script. Please believe us, it's real and it's not faked. OK, so the first goal was reproducing the whole crypto function, because Unicorn doesn't give you any libc, any kernel. Common function like memcopy, memclear are not available over there. So we need to provide a way for copying, clearing, and doing such stuff provided by the libc. So as we did before, please go a bit on top. As we did before, with the previous script I've shown you, we are going to set up the emulator, and we are going to set up the register and map all the images on the right offsets, because, as I said, it's important that the offset match. In example, we can have some pointer into the stack pointer which point to some function inside our library, and if the offsets are not matching, you can imagine that the flow won't just work. So after the mappings, you can see a list of patches. Most of them are just nope, and I noped a lot of stuff because, as I said, memclear, memcp are not available, and how we can replace these and having the same behavior also on our emulator. Please go a bit down. Okay, after set up the register, you can see a new line which you didn't see before, which is add uke. Please highlight it. Add uke code. Okay. This line is one of the biggest features of Unicorn emulator, and allows you to actually place a sort of breakpoint after any instruction, and it will allow us to do stuff. So it's a sort of callback on any instruction because it's not actually breaking the execution of the program. So if we go on top of the file and we check the callback function, which is hook code, you can see in example that on memcp list, I'm just calling the method memcp replace, which will just do what is the standard memcopy method doing. So please show the method. And so we are taking the source from R1, the length from R2, and moving it to R0 like the normal memcp. So if we run it now, please show the log. We will see, okay. If we run it, we will see the result, and with the log of all the memcp and memclearing it is doing. Forse finito su exploit everything you have. Okay. 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 We are going to show you, yeah, Vincenzo goes a bit forward without let me explain this, so please wait a minute and let me explain what's going on. After we built this emulator for Clash of Clans, we spent another 4 hours to create the clone of this emulator, but for Clash Royale instead. And please show the emulator for Clash Royale, which is here. Okay. Which is basically the same emulator. And this gives us the chance to understand the first important thing, which is that the encryption is not really changed because we are basically patching the same stuff, so the same memcopy, the same memclear, so the flow wasn't really changed. Highlighting that a possible change would be some mathematical operation on the key used, or something deeper inside the sodium encryption, which is actually the encryption method used by Supercell games. So this is the difference of the two results, and we can see that everything is matching because, of course, I didn't say that. When we created the Clash Royale emulator, we also asked to the Clash of Clans emulator to use the same stuff from Clash Royale. So we have something to compare the results, and this highlighted that everything is mostly the same, except that in a certain time point, something is changed, and which is here. Okay, so you can see before this line, everything is equal, and after this line, something is changed. So this gives us a first highlight of where the modifications has been done. And so how we can now understand what is changed in the deep. I've named this topic as exploit everything you have, because when you attempt to reverse engineer something, you should always take advantage of what you have and what the open source community is offering you. So in example, we took the node library of sodium encryption, and we placed a couple of console log, please show them, on Node.js. Okay. Right. Okay. Okay. So we placed a couple of console log here because we understood that this method is the one that was changed. We understood this thanks to the 2 logs you saw. And what we did now, run on node. Okay, we are going to run the node script. Okay, so those 2 keys you can see are 2 keys used during the encryption. So is basically the key which hsalsa20 is using during sodium encryption. And if we move to the next step, getting closer and closer, okay, you can see I've added a line, just a couple. You can see I've added just a couple of lines at hook code, at the top of hook code. So I'm basically asking the emulator to stop the emulation at this offset, because we already know it's not needed to go over, because something was obviously changed before. And we are asking to give us a dump of the stack pointer in order to check if those keys are inside. And if we take a look at the log, we can find the 2 keys on Clash Royale. So this is the stack pointer of my device. And we can see the 2 key, the one starting with 8C39 and the second one starting with 35. But if instead we open the log from Clash of Clans, we can just find the 8C1, which is another hint of where the encryption is actually changed. And so what are we going to do now? It's taking advantage of some other tools which are open sourced. And it's Capstone and Keystone Engine. Probably some of you heard about them. Are coming from the same developers of Unicorn Engine. And as well, we've added a couple of lines at the top of code. And we are basically asking it to give us the instructions that the emulator is executing. So this is Capstone. This is the standard way to use Capstone. Capstone will take a buffer as input and output to us an instruction, of course, for our architecture. So we are telling Capstone that we are on ARM, of course. And later, we set the initial, because if you are going to do something like this, probably your emulator will take 20 minutes to finish because of all the logs and all the things you have to use. And this is a sample of results, so you can see we have all the instruction flow. And so that you can understand that there is no obfuscation that can win against this, because we basically have all the flow without any jump blocks or weird loops. Okay. The other things in this script, please show them the main, please. Okay, go down. The read hooks. Another features that we used on this step is the memory read-write. And it's another cool feature of Unicorn that you can use to understand every time a memory address is being read or write. And as well, it will give us the value that is being read or write. So please come back to the log. Yep. Okay, if you can see the line, memory is being write at data size, and it will print us the values that is being actually written. So once you have tools like these, you can perfectly understand that it's just a matter of time to understand whatever is changed. And so we are going to let you see that we actually, ok, yes? Vai, prendilo. Cosa devi fare? Okay, we are going to actually let you see that the result of our work is working fine. Yep. So it's a bit non-trivial. It's a bit complex. The proxy I write, I will probably find a better way later. But we need to run actually two scripts, which is a node script, which will basically be the proxy, and a Frida script, which will feed it with all the network requests going in and out from Clash of Clans. Whoop. Yep. OK. This could happen. No problem. It's just a matter of restart. Sometimes Frida failed to attach at the beginning because we are just asking it to attach as soon as the process is started, and sometimes the memory can corrupt itself. So it's just a matter of retry. Right. Yep. Yep. And here we go. Of course, we can't give you a real protocol structure, actually, but you can. I think if you have a sharp eye, you can see that this message is not encrypted. You can maybe identify some integers inside, and yeah, it's pretty clear that it's not encrypted. So. One of the things that I personally like is to improve all this work once it's done. And so since we actually won this challenge 1 week ago, after spending Christmas night and the last of the year night on it, because you know when you have the challenge in your mind, there is just nothing that can take you out from the PC. We took this work, and we are now building a debugger, which is based on all this work. So it will run on top of Unicorn engine. And this is something that some of the features we are coding into it. So basically, we are just trying to recreate a sort of GDB, which will run on top of Unicorn to probably use it on any games which we will meet in future, which will bring any kind of obfuscation or protection, which make non-trivial to understand the program flow. Let's slide. So, yeah, I think I have 6 minutes left. And the slides, I'm not going to speak about that. This is a recap of the challenge I had with Supercell, with all my stuff being available open source. So please, if you are interested, take it a look, and feel free to meet me or meet Vincenzo on our Discord to discuss them, and also to understand in the deep how they are working. Thanks. I finished. Thanks. Thank you so much. And sorry for the English and the problems we had. Those are our references. If you want to get in touch with us, feel free to join our Discord anytime to share your knowledge with us, because we are always happy to help and share our knowledge. Thank you so much. Thanks. Any question about this? I hope that you have understand everything. I try to make things very easy. Cool. Nice. Thanks for no question. Thanks. Thanks for understand. I think that's okay. Well, enjoy the rest of the event. Have a good afternoon.